Hello all, welcome back to my YouTube channel all about VLSI. In this video, we are going to solve the problems of HDL bits. So this HDL bits. It's a very good website where you can practice Verilog related questions. So I'm going to show you how to open this and how to solve the problems, and let us try to solve the problems. Okay. So you can follow this video. You can see the question and you can pause the video and you can answer and you can cross verify with my answer what I'm doing. Okay. So that is the procedure we are going to follow here now. And this is the website you are going to open and you can register here. So I'll log in with my username and I've given my password, everything. Okay. And afterwards there is something known as problem set, and go to something known as browse problem set. Click on it, browse problem set. Yes, so this problem set has been opened. So we have different type of problems: vectors, module, procedures, circuits, combination circuits, multiplexers, arithmetics, Karnaugh map, sequential logic. These are all the topics which we are going to have. Let us try to solve them one by one in this video. So let us start with this very first one, that is getting started. So they have given all the things about this particular getting started, what do you mean by HDL, that particular description they have given, and how to write a code. So the easiest way to write your code is to do so in a code editing box. So they have given everything, and how to compile, how to simulate, everything they have given. So basically let us see how to write our code. So the easiest way to write your code is to do so in the code editor box below. For the problem, we have filled in most of the code for you already. Go ahead and finish the code in the circuit. Okay. After writing our code, we are going to press on click simulate to compile and simulate our design. Okay. So compiling, that is nothing but logic synthesis. Our code is compiled using altera quartus to produce a circuit. So quartus produces a large number of messages. Click show quartus messages to show or hide them. So it is good practice to reduce the number of warnings, but it's sometimes not practical to remove them at all. This is the way we are going to compile, and the quartus prime is the compiler we are going to use here. And coming to simulation, so our compiled circuit is simulated to test whether its functionality is correct or not. So HDL bits uses model sim to simulate our circuit. So it is going to use a model sim circuit for simulating our circuit, and then compares the outputs of the models. The simulation reports, we will get two things. First it is going to report whether our circuit matches with the reference circuit or not, or how many mismatches occurred. So a mismatch is a number of samples where the output of your circuit is not matching with the reference output. That is, our desired output is not matching with the actual output. Okay. And it may also produce timing diagrams and show you the circuit outputs when running our test vectors. So the simulation waveform is grouped into three sections: input, US, and reference. In a correct circuit, US output will be the same as reference output. If our circuit functionality is correct, our your output is same as your reference output. Okay, so the mismatch signal tell us you which sample have a mismatch. Okay, so that is the thing. And if your circuit was correct, you will see the status as success, and there are few possibilities also, like compilation error, simulation error, and incorrect success messages. Okay, and we can also track our progress in my stats page. You can check it out. Okay, so this is the instructions which they have given now. So afterwards we have a problem statement. So in this particular problem statement, we are going to start with a small bit of HDL to get familiar with the interface used by HDL bits. So the description of the circuit you need to build for this exercise. So build a circuit with no input and output. The output should always drive logical high. This is our statement which which they have given. So build a circuit with no inputs and only one output. The output should always drive one or logic high. So what can we do? So they have declared a module top underscore module output one. Okay. So for us, they have already written the code partially. So we need to write simply one here. Assign one is equal to one, and you can press on submit. So after running this, compilation has successfully completed. So, and if you want to see the quarters prime messages, you can press here, or if you want to see the log messages of model sim, you can press here, and we can see the status as success. Okay, and you can check it out the waveforms also. This is our waveform and this is a reference waveform, and mismatch is equal to 0. Okay, so this is how you are going to work with this, and this is our channel where we have also started with Verilog theory classes, in detail Verilog classes. You can go to the playlist section and you can refer our playlist. And after learning all these theory concepts, you can work with the Verilog. You can work with HDL bits. So daily we are keeping all the sessions. So from the entire basics to advanced concepts we are teaching here. So you can refer this particular playlist, and after learning this, you can work with this HDL bits for more practice. Next, after completing this, you can just click on this arrow. So next exercise will be given to you. So build a circuit with no inputs and output that outputs a constant zero. So now that you have worked through the previous problem, let's see if you can do a simple problem without hints. So here what they have given is we need to find we need to have, so here we need to make our output to a constant zero. So we can simply write it down. Assign 0 is equal to simply a 0, and you can just press on submit. Yes, so we are getting a message as successful. Now let us start with one more question. So we have a create module. So the question is create a module with one input and one output that behaves like a wire. So unlike physical wires, the explanation they have given everything. So this explanation you can check it out in our channel also, the playlist we have provided. So in this particular playlist you can check about this Verilog data types, RegNet, everything you can check it out. And after watching this particular video, you can come back and you can work with this HDL bits. Okay, so explanation everything is also present in that, or else you can read from here. So after reading all this explanation, what you need to do is, this is a question, so create a model with one input and one output that behaves like a wire. Okay, so what you need to do is, have already created a model with one input and one output. Now what we need to do is, we need to assign this output to input using the assign keyword. We need to connect this output and input. So how to do that? So using an assign keyword, assign out is equal to in, that's it. Okay, and just click on submit. Okay, that's it. So whatever your input, that is you are going to get your output, and this is our reference output. Okay, and you can just click on next. So we need to create a module with 3 inputs and 4 outputs that behaves like wire that makes these connections. A should be connected to W, B should be connected to X, B should be connected to Y, and C should be connected to Z. And the explanation for this is given. And what we need to do is, we need to connect W to A, X to B, and Y to B. That means here our X is having the same driver B, and Y is also having the same driver B, and Z is connected to C. This particular connection we need to make it out in this particular code. So how to do that? Using the assign keyword, we are going to do that. Assign W is equal to A, and assign X is equal to B, X is equal to B, and assign Y is equal to B, and assign Z is equal to C. This is what we are going to do, and just simply click on submit. So the status is success. Okay, and you can verify your waveforms also. This is our input, and this is a waveform which we have written, and this is a reference waveform. So both are matching. That's why we are getting a status as success. And you can just click on next. So we need to create a module that implements a NOT gate. So how to implement this? This and all we have also discussed in our playlist. You can refer this in the gate level modeling. Here in this particular video we have discussed it. So the circuit is similar to a wire, but with slight difference. When making the connection from in to the out, we are going to implement an inverter. So how to implement this inverter? Using the assign statement, we need to do that. So we need to add an assign statement so that it will implement a NOT gate. So how to write that is, assign out is equal to NOT of in. Okay, so like this you can implement so that your NOT gate will be created. Just click on submit, and status is success. Okay, and just click next. Now we need to create an AND gate. So all these operators we have discussed in our playlist, so you can check it out in the operators section. NOT gate, AND gate, bitwise operators, logical operators, this and all we have used. So for getting this AND gate, it is a logical operator we should use, or you can also use a bitwise operator. Since this is only 1 bit width, right? So you can use any operator. Assign out is equal to A. I'm using a logical operator and click on submit. Okay. So this is the input waveforms and this is our waveform and this is the reference waveform. So both are getting matched. So we are getting a success message. Next, press on next. We need to implement a NOR gate. Next, we need to implement a NOR gate. So how to implement a NOR gate? This also we have seen in our sessions. So assign out is equal to comp. Okay, status is success and just click on next. We need to implement an XNOR gate. So how to implement an XNOR gate? Simple again. Out is equal to A XOR with B. This is our XNOR operation. And assign out is equal to. Click on submit. So here the circuit so far we have implemented been simple enough that the outputs are simple functions of the inputs. Our circuit becomes more complex. We need to connect different wires. So we need to basically make this connection. So we need to connect these two NOT gates. So for connecting these two NOT gates, we need to use a wire. So that thing we have discussed here when we are discussing about the port connection rules, we have discussed in that. So how to do that, we'll see. So we need to make this particular connection. Okay, so how to make this connection? So first of all we need to have a first of all we need to decide how many wires do we need. So for connecting these two components we need one wire, and for connecting these two components we need one more wire, and for connecting these two components we need one more wire. So total three wires we need. Okay, so let me declare those three wires. Wire W1, W2 and W3. So these are my three wires which I have declared. And now this W1 is my output of my AND gate. So simply I'm going to write assign W1 is equal to A and B. Logical AND with B. And this W2 is nothing but C AND with D. Assign W2 is equal to C AND with D. And my output of this OR gate is nothing but W4. Assign W3 which is equal to C OR with W1 or with W2, and assign output of my NOT gate is out underscore N. So assign out underscore N is equal to input of your NOT gate is W3, and assign output of my OR gate is directly connected to out. Assign out is equal to W2, W3. Okay, so this is how I'm making my connections, and let me click on submit. And here my out underscore N is complement of W3. This I need to write it down. Yeah, now let's check. Okay, so we are getting a success message, and these are our inputs and this is our output, and reference output is this. So both are matching. We are getting the message as success. Now let's check next one. So we need to, the 7458 is a chip with 4 AND gates and 2 OR gates. The problem is slightly more complex than 7420. So we need to create a model with some functionality as 7458 chip. It has 10 inputs and 2 outputs. We may choose the assign statement to drive each of the output wires, or you may choose to declare 4 wires to use an intermediate signal where each internal wire is driven by the output of AND gate. So we need to basically implement this particular design. Okay, so let's see how to implement this. So inputs they have already declared, and outputs also they have already declared. Now we need to declare wires for making this intermediate connections. So how many wires do I need for making this intermediate connections is, for connecting this and this component I need one wire, and this component I need one more wire. So two wires. and this component third wire, this and this is fourth wire. So total I need four wires for connecting this wire W1, W2, W3, W4. Now afterwards, what should I do is I need to make the connections. So my output P2 underscore Y. So first of all, let me get the output of this AND gate. Let's say it is output of that AND gate is assigned W1, which is equal to, what are the inputs of this AND gate? P2C, P2D, P2C and with P2D. So assign W1 is equal to, we are getting this, and this OR gate is having, next let us see this AND gate output. Let's say it is W2. Assign W2, which is equal to P2C and P2D, and this AND gate is P2A and P2B. Let's say it is P2A and P2B. Next is P2C and P2D. So I've written the logic for this AND gate and this AND gate. Now these two outputs are given to this OR gate, and the output of OR gate we can see from here, it is P2Y. So assign P2Y, which is equal to W1 or with W2. So I've got my P2Y, and coming to this P1Y. So coming to this P1Y, first we need to implement this AND gate. So coming to this AND gate output, let's say it is W3. So assign W3 is equal to P1C, P1B and P1A, and operation between P1A and P1B and P1C. This is my output of my AND gate, and coming to this P1F, E and D. So assign W4 P1E, P1E F D, DEF, and with D and F. So these are my output of my output of my this AND gate. So output of this OR gate is P1Y. Assign P1Y, which is equal to W3 and W4. W3 or with W4. Okay, this is the code for this logic. Let us submit it. So we are getting a success message. Now let's check for next one. So next concept is about vectors. So vectors also we have discussed in our playlist. You can check it out here in the port connection rules, and in Verilog data types we have discussed that particular concept of vectors. So you can also check for this theory, or else you can refer our playlist on the vectors. Now in this particular case, what they have asked us to use a vector. Here the 3 bits should be connected to this out V. The input is directly connected. The input 3 bits are directly connected to the output, and O2 is connected to the MSB bit of this VEC, and O1 is connected to the index 1 bit of VEC, and O0 is connected to VEC LSB. Okay, that we need to do that. So how to do that? So we can write it simply, assign out V, which is equal to VEC. Okay, and assign O2 is equal to VEC of 2, and assign O1, which is equal to VEC of 1, and assign O0 is equal to VEC of 0. So this is the thing which we have written. Okay, let me submit it. Yes, so it's a success message. Now let's see next one, vector 1. So vectors are used in the theory they have given. Okay, so what we need to do is build a combinational circuit that splits an input half word into lower and upper bytes. So this we need to do that. So basically we have an input of 16 bits. We need to divide it into lower 8 bits and upper 8 bits. So assign out underscore higher, which is equal to in of 15 down to, and assign out underscore lower is equal to in of 7 down to 0. That's it. Okay, let me submit it. Okay, this is our success message which we are getting. Now next, let's see another question, vector 2. So in this vector 2, what they have given is, so the operation is often used in an NDNS. So vector can be viewed as containing 4 bytes, bit 31 down to 24, 23 down to 16, etc. Build a circuit that will reverse the byte ordering of the 4-byte word. For example, A, B, C, D should be written as this should be present at the MSB, followed by A should be present at the LSB. So this we need to do it. So how to write it down is, so they have given the hint also for us. So assign out of 31 down to 24, which is equal to in of 7 down to 0, and assign out 23 down to 16, which is equal to in of 8 down to 15 down to 8, and assign out 15 down to 8, which is equal to in of 23 down to 16, and next assign out 7 down to 0, which is equal to in of 31 down to 24. Okay, let me submit it. Yes, so these are our inputs and this is my output. So whatever the MSB which is present, that is copied to the LSB, and LSB content is copied to MSB. Next, let's see next one. So vector gates. So build a circuit that has 3 inputs that compute the bitwise OR of the 2 vectors, the logical OR of the 2 vectors, and the inverse of both the vectors. Place the inverse B in the upper half of the outer underscore naught and the values of A in the lower half. So basically what we need to do is, A and B are of 3 bits width. So A and B are of 3 bits width. So we need to place the inverse of B in the upper half of out underscore naught. So out underscore naught is basically 5 down to 0, that is total 6 bits. So we need to place this upper half, that is 5 down to 3, should be filled with out underscore naught, that is this output, and the lower half of this out underscore naught should be filled with this inverse of A. Okay, so upper half should be built with inverse of B and lower half should be built with inverse of A. So first of all, let us try to get this out underscore or underscore bitwise. Assign out underscore or underscore bitwise. Here they have mentioned bitwise operator. Bitwise operator we have discussed in our operators session. What do you mean by bitwise operator and what do you mean by logical operators? What is the exact difference between the bitwise and logical operators that we have discussed? Okay, so this you can once verify it. Okay, so what we can do, we should simply write A or with B. This is the bitwise OR operation between A and B. You're not supposed to use logical operator here because your output will be a single bit. You should use a bitwise operator here. And one more thing is out underscore or underscore logical. Assign out underscore or underscore logical. Here you are supposed to use a logical operator, and they have specifically mentioned a logical OR operator. So how to use your logical OR operator? Simply A logical OR with B. Okay, this is your logical operator. And this out underscore not, coming to this assign out underscore not, it is equal to so in this out underscore not also 5 down to 3 bits should be filled with not operation of B. So it is simply bitwise not operation of B, and assign out underscore not of last 3 bits 2 down to 0 should be filled with bitwise not operation of A. This is not logical operation. This is bitwise not operation of B and A. Okay, let's submit it and let us check our outputs. So we are getting output as success. So this is how we are going to deal with our normal logical operators and bitwise operators. Now let's move to the next one. So we need to build a combination circuit with 4 inputs and there are 3 outputs: out underscore and, out underscore or, and out underscore XOR. So out underscore and is an output of 4 input AND gate, and out underscore or is an output of 4 input OR gate, and out underscore XOR is an output of 4 input XOR. So what we need to do is we need to simply perform AND operation, OR operation, and XOR operation. So assign out underscore AND is equal to in of 3 and with in of 2 and with in of 1 and with in of 0, and assign out underscore or which is equal to in of 3 or with in of 2 or with in of 1 or with in of 0, and assign out underscore XOR which is equal to in of 3 or with in of 2 or with in of 1 or with in of 0. Let me submit it and let's check. And output XOR, sorry, here output XOR is, here output XOR gate we have used a different symbol. This is our XOR gate. So we are getting a success message. So what are we doing here? Simple. So this is how we are going to deal with our 4 input gates. Next let's see next question. So if you want to learn all these concepts in more detail, you can visit our Verilog HDL playlist. We have discussed this particular things. You can visit and you can learn all these concepts. Next, so part selection was used to select a portion of vector. The concatenation operator is used to create larger vectors by concatenating smaller vectors together. This also we have discussed in our playlist in this logical operators shift and concatenation thing. So you can refer that. So a bit of practice: given a several input vectors, concatenate them together, then split them up into several output vectors. There are 6 5-bit input vectors for a total of 30 bits of input, and there are 4 8-bit output vectors. The output should be concatenation of the input vectors followed by 2 1 bits. Let's see what they are saying. So they are basically 4 8-bit output vectors W, X, Y, and Z for 32 bits of output. Okay, the output should be a concatenation of the input vectors followed by 2 1 bits. So here they have given output widths of 8 bits. W is of 8 bit, X is of 8 bit, Y is of 8 bit, and Z is of 8 bit. And whereas your inputs are only 5 bits. A is 5 bits, B is 5 bit, and C is 5 bit, and D is 5 bit, and E is 5 bit, and F is 5 bit. And we need to concat this. W is 8 bits, and this is only. So what we should do here is assign concatenation of W comma X comma Y comma Z, which is equal to concatenation of A comma B comma C comma D comma E comma F comma 2 tick binary 1 1. That's it. So basically this output is 32 bit and this is 30 bit. So we are appending 2 more ones to make it is of 32 bits. Let us submit and let's check. Okay, so we are getting a success message. Yes. Now let's check for next one. So given an 8-bit input vector, reverse its bit sorting. So we need to reverse this particular vector. So we have module input 7 down to 0 in and output 7 down to 0 out. So we have an input 8-bit vector. We need to reverse its bit ordering. So how to reverse its bit ordering? Let's check. So what can we write here is assign out is equal to concatenation of in of 0 comma in of 1 in of 2 in of 3 in of 4 in of 5 in 6 in 7. Okay, so like this you can reverse your bit order. Let us submit and let's check. Okay, so this is how we are going to reverse our bit order. Next, so that is how we are going to solve our questions, and that's all about this particular video. So if you like this particular video, please like, share and subscribe to my YouTube channel all about VLSI. If you want me to do this type of problems, more type of problem solving sessions, please let me know in the comment section. Okay, yes, so that's all about this particular video. Thank you for watching this video.